Big Bang happened where you're standing. The Big Bang happened everywhere. Every point in the universe is part of the Big Bang. Now, imagine taking all the stuff in the universe, all the stars out there, right? All the planets, all the stars, and we go back in time. The universe, if you go back in time, was smaller, right? All the stuff in the universe, all the galaxies, all the stars were way more closer together in the past. The universe, in other words, was compacted into a very small volume, relatively speaking, smaller than today's volume. Today, the universe is billions and billions of light years across, right? But in the past, the entire universe, all the stuff in the current day universe, was compressed to a volume the size of a fruit, right? The size of an orange or a grapefruit. So imagine how hot that universe was back then, 14 billion years ago, right? So this diagram is expressing what that means. If we go back in time, we see a universe that's smaller, hotter, denser, right? That's what the Big Bang was. A moment in time when the universe was super duper hot. We're talking millions of degrees, right? Potentially even billions of degrees. And at those temperatures, right, at that configuration, it was extremely different than today's world. I mean, the current laws of physics don't work. They don't work at those temperatures, right? They don't work at those volumes or temperatures. So this is where all of our knowledge stops. The Big Bang is where all of our knowledge about the universe stops. It's the end of what we know, not the beginning. The Big Bang is not the beginning. It's the end of what we know. So, at the Big Bang, the universe expanded. Why is it expanding? There's dark energy in the universe. Space and time is full of this dark energy that wants to pull it apart. Like a rubber band, it's stretching and pulling itself apart. And that's what we are today. We're in a time where the universe is now expanded and much larger than it was billions of years ago. Now, the evidence of this is a few pieces of evidence for this. Number one is the CMB radiation. And this is radiation from this moment, 13.9 billion years ago. Right? That radiation was emitted and went out into the universe and filled all the universe. And now we are able to see that radiation. But it is now in microwave form. It's why it's called the cosmic microwave background, right? But in the past, it was likely in a very much more higher energy state, perhaps ultraviolet or perhaps even X-ray. That's the evidence that there was one time this extremely powerful event that happened. Right? That's what the CMB is. Now, another piece of data for the Big Bang is the red shifting of galaxies. When we look out in the universe, we see a bunch of galaxies. And we see that the light from them, it's kind of elongating. The light is getting stretched. And the reason why is because the universe is stretching. Right? So all this data corroborates to the universe being way bigger in the past. And way smaller in the past, way smaller, and now expanding to a way bigger universe today. Everything's stretching. And that's all the Big Bang means. In a way, the universe is stretching apart. And now here we are today in a universe that's way less compacted. Galaxies are far apart from each other. And we're moving away. We're still expanding today. The expansion is seemingly speeding up a bit. And the reason why is because there's no longer all that mass getting in the way of dark energy. Dark energy wants to pull, gravity wants to bring in. And now we are finally able to expand. And that's where we are today. Okay. So let's get the next slide. Okay. So let me talk about the first stars, right? How did the first stars form? How did our Earth form, right? I'm going to get into that now. Okay, let me see. Sorry. All right, so here's a picture of the Big Bang again, the diagram. If you notice, at the Big Bang, there was lots of gas and dust. All right, as far back as we see, there was this weird plasma kind of material. It wasn't even like matter we know today. It was a very hot material called a quark gluon plasma. But after that, after the universe cooled, as the universe expanded, it cooled down and allowed for that matter to condense into gases like hydrogen and helium. These gases made up most of the universe back then. Most of the universe in its early time was just gas. And dark matter is what makes up most of the universe. Dark matter is invisible. Now, dark matter is invisible to us today, right? Because we don't see, it doesn't interact with light at all. But it makes up most of the mass in the universe. It's something invisible to us. When I'm talking about the gas, I'm talking about visible matter. So the hydrogen, the helium that you're made of, that the universe is made of, is only about 5% of the mass, 5% of the matter in the universe. So dark matter, even though it's invisible, it kind of collected those first gas clouds together into the first stars and first galaxies. Now, how did this happen? Well, these gas clouds that were collected due to dark matter, these gas clouds collapsed due to gravity, right? Gravity, they attracted to each other due to gravity, and these clouds collapsed into disks like this. Now, what happens is, because of the way the gravity collapses these nebula clouds, they start spinning because of something called angular momentum. They start spinning, and they gain momentum in this process. In this process, a lot of mass, that heavier material, gets stuck into the center, right? It gets pulled into the center. Kind of like when you're, having a cup of coffee, right? And you're swirling the spoon inside, right? That's causing the stuff in the center to build up in a way, right? And that's what happened here. As this cloud started to spin into a disk, all this stuff collected into the center. And all that stuff collected and it became hot. Gravity pulls things in, and this squeezes the stuff inside and making it compacted and hotter. Why is it hot? Temperature rises because it's so compacted. The molecules that are bumping around are moving very quickly. They're bouncing around very quickly. And that's why it was so super duper hot back then in the star. And that star started to form a larger star. And it accumulated more matter, accumulated more stuff, more debris. And it got bigger and bigger and bigger until it turned into a protostar. And this protostar is what gave rise to our sun. And the reason why it gives off light, right? The reason why this protostar gave off light is because of nuclear fusion. Nuclear stellar fusion. Essentially, atoms and material are bouncing around so quickly inside the core of the star that it kind of ignites. It kind of emits. Those two atoms, like two hydrogen atoms, can fuse together. And in the process, they emit light and energy and all kinds of particles. But light is what we care about. We care about the visible light, right? The ultraviolet light, the infrared radiation, the heat. So this is the beginnings of our sun, about 4 billion years ago, 4.5 billion years ago. And as the star grew older in age, in its adolescence, the star began to emit a shock wave. So stars typically love, in their adolescence, emit shock waves, X-rays and gamma rays and UV rays. And this shock wave pushes material outwards. And all that stuff on the outside of the star, right, in this gas cloud, it condensed, it precipitated into heavier material, heavier fragments. little crystals, little rocks, right? Sand grains. And these little grains collected due to gravity. As they spun around this disk, they collected, they formed smaller rocks, right? Rocks, material, and all kinds of gaseous material. They form due to gravity little planetesimals, tiny planets, right? Tiny planets form. They precipitate, much like rain precipitates in clouds. As it gets colder, what happens? As the rain, the water evaporates into the air. It gets colder as it goes up, and it condenses into crystals. And that's what rain is. The same applies to the stuff in the early solar system, right? The planets that you live on are rocks, big rocks, and big gaseous stuff, and they collected, and that's the origins of our planet Earth, right? All these smaller rocks became clumpier and became bigger and bigger rocks and made us. Now, again, these rocks are very, very hot. So let's get to the next slide here. Are you guys enjoying it? So here we have our early Earth, right? It was a big rock. It's molten, though. The reason why it's so hot is because it's been bombarded by tons of material, right? It's being bombarded all the time. There's so much stuff, and it's swirling around in this big, witch's brew of material. And what we see is a very hot ball, which is the early Earth. It was literally liquidy. It wasn't even solid at this point. It was very liquidy because it was so hot. The metals that make up, stuff in your phone were there, but they were super hot. They were molten. That's how hot it was back then. And over time, it became bigger and bigger, and eventually all that stuff slowed down. The bombardment slowed down. There's over time, gravity makes things more organized. And here we go. We have the early Earth. But then about 4 billion years ago, a planet smashed into the Earth. A planet the size of Mars called Theia smashed into the Earth. Our planet was bombarded by this big planet. And a large chunk of the debris, the ejecta, turned into the moon. A planet smashed into the Earth. A large chunk of Earth got spit out. And that stuff that got spit out went into orbit around the Earth and became our moon. As it cooled down, it became the moon. And we know this now because we went to the moon and we actually discovered rocks from the moon, and we found that they're very similar to the stuff on our planet. As well as the fact that we see around the world, around the moon, is very homogeneous in terms of its surface. It's a very homogeneous surface. Is the key indicators of a very molten past. So, but after that, the Earth began to get more spherical as time passed on, as more debris started bombarding it a bit more. And some of the asteroids that smashed into the Earth were called carbonaceous chondrites. And these rocks, inside of these rocks, contain water in ice form, or hydrates in rock form. Water is a very common material in our early solar system. It was very common, and it's found a lot in these rocks. And these rocks that bombarded the Earth are what gave rise to our oceans. These rocks that contain all these solid water and these hydrates, they smash into our planet. They evaporate, they vaporize, and turn into gases. And these gases then go into our atmosphere. They make up our atmosphere. And over time, as our atmosphere and our planet cool down, because that's what things tend to do, the heat tends to leave into space. And our atmosphere collected, and Earth got colder enough for that vapor to condense into oceans. So, because of all the mass on the Earth that has gravity, right? that gravity is holding in the atmosphere. And that's what allows us to breathe, right? All that atmosphere, all that gas is coming from that stuff in the earth. Now, so here we have, about 3.8 billion years ago, we have a very warm, semi-warm planet just below, melting point, just below boiling point, 100 degrees Celsius. Earth was about 90 degrees Celsius here on average. And you have liquid water on the surface with an atmosphere, a very small, thin atmosphere, but still there. And the first living organisms emerge about 3.9 billion years ago. Now, how did that happen? Well, let's talk about abiogenesis. So, deep in the Earth's oceans, right, as these oceans form, a lot of salts mix in with it from the Earth's crust. A lot of magma activity, a lot of volcanic activity is occurring at this time because the magma is still seeping up into the surface. Pressure is forcing that stuff into the surface. The plates are now beginning to form. The crust is beginning to solidify and turn into plates. And sometimes magma can seep up from these plates. And on the bottoms of the oceans, right, in the near surface of the ocean, the bottom of the oceans, on the floor of the oceans, we see this separation of these plates, and sometimes there could be areas where there's a lot of heat that comes from the underground, and these are called hydrothermal vents. Hydrothermal vents, and this is where a lot of chemical activities are happening. Right, we have lots of all kinds of amino acids forming, right? A lot of carbon, a lot of stuff from underground, iron, right? A lot of different chemical compounds, very rich in chemical and very diverse in its chemical compounds. And this also is emitting heat. It's warm down there. It's very warm down there. And it's smoky, right? That smoke that you see is full of all those chemical compounds. So it's warm, it's smoky, and full of ingredients. Ingredients like amino acids. These amino acids, these are the building blocks of life. It's what makes up you and me. Our cells, our skin, our eyes, our brains, our hearts are made of these very simple molecules. And what happens is these very base molecules called amino acids, they can clump together, they can interact with each other and bond together. That's what carbon molecules typically do. Carbon is a very reactive element, and it loves to stick with other carbon atoms and other carbon molecules. So if you have a certain configuration of carbon molecules, such as amino acids, it's a very reactive compound. So they tend to clump together and form peptides. Right? These are longer forms of amino acids. And essentially these peptides can form longer peptides called polypeptides. They form chains, right? Long chains of peptides, long chains of amino acids. And eventually you get something like amyloids. These are sheets of polypeptides. So these polypeptides can clump together, and those can form sheets, entire sheets of amino acids. And once you get a sheet like this right here, if you can see it, you get a sheet like and these are called amyloids. Now these amyloids, when they get long enough, they build upon themselves. They build and build upon themselves, right? As we said before, they're very reactive. So they're building, and they break off. At some point, it breaks off. It gets too long, and they break off. They separate. However, those two compounds that break off from one another, those further can then build again. So what we have is a very interesting sense of replication, a very proto-replication process, right? You have these molecules build upon themselves, and then break, and then they can build even further. And these amyloids can produce their own reactants. They can produce amino acids further and further, and this could go on for as long as it needs to. And this is called a chemical evolution. And this is what happened. Various molecules in various conditions did this. And this is where life comes from. Everybody asks me, where does life come from? How do you get life from non-life? This is it. This is the beginnings of life. It's a process of chemical evolution. And it's much more complex than this. So this is a very simplified version. But we also have another example of the first protocells. It turns out that in those oceans, stemming from amino acids, are also lipid molecules. These lipid molecules can form sheets of bilayers. They themselves can form sheets they're called bilayers. The reason why, if you can see, these sheets have two different molecules on them, right? They're made of two different molecules. The reason why is because of the polarization of these molecules. The polarizations, they're opposites, so they form these sheets. But in the waters, these sheets are able to do this. They form spherical structures. And these spherical structures form the first protocells. These are the first protocells that were on the planet. And when you get the combination of all these ingredients, amyloids, right? Amyloids, protocells, lipid bilayers, amino acids, when you have these ingredients, you get the first living organism, the first cells on the planet 3.9 billion years ago. This is how the first living organisms got there. And now here we are today, right? We have way more diverse selection of animals and plants on the planet. So those first protocells, they replicated. We also have things like RNA. RNAs are also what drove this replication process. RNA inside these cells. RNA is made of nucleotides, nucleobases. Those are made of what? Amino acids, right? It's a very, very particular combination of these particles and compounds that created life. And once you have the first self-replicating molecule, cell, then you have life. That's evolution. Natural selection takes over. The survival of the fittest, the ones who are fit per their environments, they survive more, and those pass down their genes. And the information of your genes and DNA is stored in these RNA molecules or these DNA molecules in terms of their patterns, in terms of their configurations. It's a very interesting process. It's very difficult to teach, though, without going through a whole lecture. But yeah, so from that first replicating cells, right? The first cells on Earth, bacteria, about 3.9 million years ago, evolution begins. We have the first, multicellular beings, multicellular life about 3 billion years ago. For the longest time, life was asexual. It produced by itself without two different sexes. But eventually, over time, as this evolution process occurred, different sexes emerged, different types of cells emerged, allowing for animals to be produced. So we go from bacteria to multicellular life to the different types of worm and insect-like species in the oceans. Life was mostly in the oceans for hundreds of millions of years. And then the first fish about 600-700 million years ago. And these first fish is what allowed us to be here today. The first fish had the first fossils, the first bone structures, right? The first bone structures. The fins, which gave rise to arms later on. So over time, we have this very elaborate evolutionary process. And from those fish, about 300 million years ago, we have Tiktaalik, one of the first land animals that made its way to land. Why? Because of predation, right? Predators were trying to get after it. It likely laid eggs on land. So it was forced and pressured to, over time, over generations, move into the land. Now, those first bacteria, there was no oxygen. When the first living organisms emerged, there was no oxygen on the planet. There was no breathable air for us. And they produced through, photosynthesis, things like that, but they produced through the sun's energy. They lived on films on the surface of the ocean, bacteria. And they would get energy from the sun, and they would produce oxygen in this process. They would suck in CO2 and all kinds of gases and methane, and they would emit oxygen. And there was a ton of it. So this bacteria emitted tons of oxygen into the atmosphere for hundreds of millions of years, right? And that's what gave rise to the current day atmosphere, right? That's why we breathe oxygen today. We are literally breathing in the farts of bacteria billions of years ago. And it's just been recycling over time, forever. It's the same oxygen that you're breathing, that's going through your lungs right now. It's the same oxygen that bacteria farted out 2 billion years ago. Okay. So, 300 million years ago, Tiktaalik, the first land animals, but also at this time were the first trees. Trees are new to the planet. Trees are brand new. 300 million years ago, 350 million years ago, the first trees emerged. And these trees gave rise to habitats for these animals, right? For the longest time, animals that even attempted to be on land would die quickly. There was no habitat. There was no way they would survive. But trees gave the ability for these animals to feed on these plants and trees. It gave rise to habitats so they can live near these trees. And that's what they did, right? As more and more animals left the oceans and lakes and water to land, you see them evolve further in more drastic ways than ever before, because there's a way more expansive environment out in the open. Okay, the first eyes emerged. The first eyes that can see far emerged about 250, 300 million years ago. For the first time, beings can now see far away. It's infinitely far in front of you. So we have the first mammals about 300 million years ago. They emerged from those amphibious creatures, the first mammals and reptiles. And 250 million years ago, we have the shrew-like animals that emerged from the reptiles. They live near trees, right? They were mainly herbivorous, some carnivorous. The dinosaurs, 200 million years ago, the dinosaurs emerged. And for, 200 million years, they reigned on the planet. They were the dominant species for hundreds of million years, way longer than we have been here. But, of course, we all know about 65 million years ago, this big asteroid, this big rock smashed into our planet, lifting up tons of debris and dust, blocking out the sun. And the dinosaurs couldn't adapt fast enough. They died. 75% of all life died 65 million years ago. And some of them survived. Some of the dinosaurs survived. The mammals survived as well. And those mammals, those shrew-like animals, gave rise to monkeys and, apes like we. Those apes, those monkeys adapted and lived near trees and lived in families, and they were tribal animals, and the apes emerged from them. And here we are today, human species. And some of the dinosaurs that died are today birds. Birds are dinosaurs. Every bird, every chicken, every ostrich, every bird is a dinosaur. Now, so you can see that this picture shows you a line, a very linear line. That's not really how it works. Evolution is more like a tree. Think of evolution like a tree, where you have a stump, a common stump right there, and it branches out to different branches. And each branch is a new species. Every branch of the tree of life is a new species. And we are just one branch of the tree. And there's different ways of new species emerging, right? Sometimes if you have a common species, populations split, and those split populations go their own ways. They split into different branches over time. Sometimes they come back again and reemerge and, form new species. There's many different pathways for speciation to occur. But the basic part is it's like a tree. It branches out. And it's always branching. Evolution never stops. Evolution's happening as we speak, but it just takes generations. It takes time for genes to get passed. It takes time for new species new populations to use those genes and, survive versus their counterparts. Now, some of the best evidence for evolution is in our bones, our bone structures. And what a great way to look at our past, by digging up the earth, looking through the geological strata, the layers of the earth, and finding fossilized remains of our ancestors. And we do all the time. Interestingly, one of the most stark examples of evolution is Abiogenesis. Abiogenesis was all right, let me start from the top. One of the most stark examples of evolution are whales. Whales are mammals. They're not fish. Even though whales spend all their time in the water, they're not mammals. Why is that? That makes no sense. It would make no sense for whales to be mammals if, they were like the fish, how they got there from the... No, it's a very different process. For the longest time, it was a mystery. We see whales give live birth. That's weird. We see whales with nostrils like ours and noses kind of like ours that breathe air from the outside world. That's weird. Fish don't breathe air from the outside environment. They absorb oxygen in their gills from the water that's dissolved in the oceans. But whales don't do that. Whales have to go up and breathe the air from the outside. We also see vestigial structures, remnants of hip bones and leg bones in whales. Why is that? That's been so mysterious for so long. And we now know why. We've discovered that whales come from four-legged animals about 60 million years ago. Abiogenesis. And this is a fossil we have. We have this guy, his name is Abiogenesis. We found him near Pakistan. That's why he's called Abiogenesis. But near the areas of Pakistan were once 60 million years ago very low-lying areas of water. And these Abiogenesis, these kind of like, they look like dogs. They would run, they would walk they would live near the waters. And over time, they would slowly get more aquatic. As they went deeper into the waters and lived longer in the waters versus land, they would become aquatic. They would grow webbed feet. They would, over generations, they would have webbed feet. They would live longer in the waters. Their noses would be longer so they could more easily get the air. Their tails became elongated, allowing them to swim better, more stable. And they became aquatic species like, whales, modern day whales. And we see the remnants of this That's why. That's what perfectly explains why they have leg bones and hip bones. It's because they were once four-legged animals. So this is a prime example of macroevolution right in front of your eyes. Okay. We also have lab experiments where we can take a look at bacteria that evolve over time. They speciate. And we also can take a look at your DNA. We can see the changes in your DNA, the mutations that occur, right? Mutations occur when certain genes get misplaced, certain nucleotide bases get misplaced, or proteins, or things like this. When your DNA replicates, errors occur. And these errors can accumulate and turn into things like we. We are the remnants of billions of years of those errors and changes that happen in our DNA. We are the end of the thread of life, the thread of evolution that has never stopped, right? The tree that it's never stopped branching. That's what we are today. We are the remnants of our past, our ancestors. So if you go back all the way into the past, all those branches, all the species on the earth, every animal, every plant, every fungi, every living being that has ever lived, you trace all their lineage back and you find a common stump about 4 billion years ago. A common ancestor of all living beings. Those were the first cells. They were way more primitive back then. There was no DNA back then. But they were living. And they gave rise to us today. And now we're here. Now we're here. We're just chilling, right? Now we're just chilling. Living our lives. Doing stuff. But it's important to understand our history. Our past. Our past is important to know and understand. To know the future. To understand who we are, to understand what we are, where we come from, right? These questions I get asked every day. Mike, who made all this? Where do we come from? These are great questions. Okay? These are great questions. But the answers, I know we don't have all the answers, but we do have some answers, and they're damn good answers. Right? And that's what science is here for. It's why it's incredibly important to learn science. Because it gives you a reference frame. It gives you a perspective of seeing the world. And it's like no other. No other perspective explains what science can. What all the things I just explained today. No other perspective can explain these things. And all the things we've learned today are the fruits of great scientists of the past, the fruits of great scientists in the past, Darwin and Einstein and Newton, and hundreds of others. So let's embrace our planet. Let's embrace who we are, right? Let's stop fighting and bickering about who made us. You do see design. Just learn about the world around you, and there's a lot to learn. And guys, there's a lot more out there than we know, than we can see and observe. There's a lot more things to learn. So let's do it. Let's learn it. Let's learn more. I hope you guys enjoyed that. Now I'll do some Q&A. Oops. Okay. Go ahead, ask any questions about the live. Thank you, Cora, for enjoying it. Our science in knowing animals, why are animals still going extinct? We're destroying their land. We're destroying their habitats. Humans have touched every square inch of the planet. Every square inch of the planet we have touched. We have somehow made worse. The Arctic, the ice is melting, glaciers are melting, water is becoming polluted, microplastics are increasing. We are destroying everything. We're desertifying the world. We are taking away trees. We're cutting down trees like crazy. In the Amazon, right? The lungs of our planet are being burnt out. What is dark matter? Dark matter is a type of matter that we just don't see with light. Light doesn't touch it. Light doesn't interact with it. But dark matter is there all around us. Right now, you have tons of dark matter moving through your body. Dark matter does not interact with our matter much. It interacts with space and time. It has a gravitational effect on us. We can feel the gravity of dark matter, but we can't touch it. We can't feel it. It's invisible. It's not there in a way that we can observe it directly, but it is there indirectly. And right now you have lots of it moving through your body. It's like the glue that holds our galaxy together. Okay, what happened to the Neanderthals? The Neanderthals they likely died because of disease, or perhaps we killed them off. Perhaps we, just killed them all off. We don't know, actually. This is one of the best mysteries in human evolution, but they died about 50,000 years ago. Human evolution is amazing in itself. How we traversed the plains of Africa, left to other continents, and have speciated after that. It's quite amazing how we evolved, how we discovered fire, how we invented tools. We used language to talk, communicate, pass down our knowledge, and that expedited our evolution. And that's what makes us human. Mike, if you say the universe always existed, then that means it can never end, based on that logic. Yeah, there's no evidence of an end or beginning. We don't know what that even means. We don't know how big the universe is. The universe could be infinite. It could be billions of times bigger than we think it is. We don't know. We don't know. What was Louis Pasteur's experiment? Louis Pasteur did not do an experiment on abiogenesis. He experimented with spontaneous generation, which is something vastly different. In the 1800s, people had no idea how life arose. They had no idea how life arose at all. And they thought, Louis Pasteur at least thought, that life could emerge spontaneously from, pre-existing material. But we know that's not the case today. I mean, it doesn't just spontaneously evolve without any, mechanism. So that's been debunked. But what has now taken over is something called abiogenesis, where we now know the chemical evolution that preceded modern primitive cells in the past. The amyloid hypothesis, the RNA world hypothesis. There's many different hypotheses that are encompassed by abiogenesis that describe how the first cells emerged through chemical processes. It's quite complex, but it's very understandable, and we've learned a lot since then. If rocks crash to the Earth carrying water, why haven't we found planets near us with water? We have. Every planet has water around us. In fact, every planet in the solar system has water in it. Mars has tons of water in its poles. Locked in its polar ice caps is tons of water. In fact, if you were to melt all the ice on Mars, it would be enough to cover the entire surface in 2 or 3 feet of water. There's a ton of water on Mars. A lot of the water is also submerged in subterranean soil. It's not liquid. There is no liquid on Mars, but it's ice. The moon as well. The moon has tons of water on its surface and underground in its poles. A lot of the water's in craters. Venus has water in its atmosphere. Now, Venus is 900 degrees on its surface. There's no way water can exist in liquid form. It's gaseous. Mercury probably has some water in its poles, probably. Jupiter and Saturn and Venus, Jupiter and Saturn and Uranus, all have water. All are made largely water and hydrogen. But it's gaseous, right? So the water is very common in our solar system. It's just that on Earth, the reason why we have liquid water is because our particular planet has an atmosphere, enough gravity to hold the water, and cool enough temperatures to keep it liquid. Okay? No other planet has that. No other planet has that combination of stuff. So in a way, we are special. The only planet with liquid water. Now, on its surface, we are the only planet that has liquid water on its surface, but under the surface of moons of Saturn, like Titan and Enceladus in Europa, there may be tons of liquid water. On Enceladus, there's tons of water. In fact, it's a big snowball, essentially. It's made of ice. On the surface is full of an icy crust, about 30 miles thick. But under the ice, if you were to dig with a big drill and dig into it, you might find an ocean of water that is larger than even, entire, about 1 to 5% of the water on the Earth. On certain moons like Ganymede and other moons, there may be more water than the Earth has in liquid form. But the point is, there's a lot of water out there, and it's just that we are special in the sense that we have it on our surface in liquid form. Okay. Do you think humans will figure out how the universe works? We are. We're trying. Do I have any degrees in science? Yes, I do have a degree in geoscience. Thoughts on the Iliad argument? It's nonsense. What evidence can you provide with our 5 senses? What do you mean? For what? How did gravity come to exist so that we could live on this beautiful planet made for us? Well, nobody said or knows if the universe was made for us. That doesn't seem to be apparent. It seems, in fact, the utter opposite. It seems like we adapted to the Earth that was already here. It wasn't made for us. We adapted to it. And that would make sense because we have adapted to the conditions. Like, for example, we have to consume food every day to survive. And, we have to drink enough water to survive. And the amount of water and food you need tends to be how much there is present in your environment. We've also developed pigmentation in our skin, which protects us from UV radiation. But just enough so that we survive and can reproduce. A lot of times the sun can damage our skin and give us cancer and disease, right? So we live within a specific parameter of conditions that are required, are sufficient for us to reproduce within it. we meet sufficient requirements to reproduce, and that's why we're here today. There is no evidence, though, that we adapted or that we were made for the planet. The sun doesn't cause cancer. It absolutely does cause cancer. Those UV rays can intercept our DNA and really give us mutations, spark mutations, causing cancer. That's what causes cancer. Okay. Is consciousness a property of the universe that rises from complex chemical reactions? We don't know what consciousness is in terms of its nature, but we do know that it seems to arise from brain patterns, brain chemistry. Neurons every cell in your body can generate electricity. Every cell in your body is alive because of electricity. It generates certain amounts of millivolts of energy, of a charge, and these charges can influence other cells, and that's what allows you to move and your muscles to change and for your brain to think. Your body is a circuit, a gigantic circuitry of they're called action potentials that move through your cells. And this is what seems to be consciousness. It seems to be that consciousness is the emergent phenomenon of all these processes happening, these electrochemical processes happening in your body. That's what it seems like to me. I don't know anything otherwise. Okay. Do you think we know we die after death? I don't know what happens after. I think you rot away when you die. No evidence otherwise. I'd love for there to be evidence otherwise, but I just don't see it. The first human on Earth, how many were there? Well, there was no first person. That's not how evolution worked. There was no first person that just popped into existence. There were no Adam and Eve, right? That's nonsense. It's like, it's a very gradual process. It's very difficult to explain without diagrams, but evolution is a very gradual process. So if you go back far enough, your father, your grandfather, his father, if you go back far enough, every person, every generation before me was another person, right? There was never a moment where you went from a non-human to a human, okay? Just like there was never a day where you became, a toddler, or there was never a day you became a grown adult from an adult, right? Or a teenager to an adult. There was no day. There was no such day. Your body just changed dramatically. It's a very gradual process. Aging is happening gradually, but consistently. The same with evolution. There was no one day where you just speciated. It's a generational process, and it happens in increments that are so subtle you can't hardly see it on a day-to-day basis. Now, humans, however, we share common ancestry with all the apes of today, all the great apes like bonobos, gorillas, chimpanzees, orangutans, these baboons. These apes are our ancestors, our cousins. Why? Because if you go far back down on the tree of evolution, you find that we share a common stump about 6 million years ago. About 6 million years ago, all these apes go back to a single ancestor, and it was an ape, well, kind of like us, but, different enough that would render it a non-human. And from that species of ape, we emerged. And other species of apes emerged and branched out. And we all went our separate ways. So from that moment, other species emerged, and now here we are. We're human. Our cousins or those other beings that look just like us. Chimpanzees are almost identical to us genetically, right? Chimps have 99% of our DNA we have 90% of our DNA in common with chimps. We are nearly identical to them. Why? Because we're relatives. We are genetic relatives. We are all family. In a way, every human being shares DNA with each other. If you go far back enough, we all share a common ancestor. The further back you go, there's more ancestors to go, right? It never ends. There's a never-ending lineage of ancestors. Okay. What can you say about the soul? There is no soul. I don't see any evidence of a soul. Now, in Latin, soul means the breath of life. And for thousands of years, people who didn't understand science thought that there was some force that made us alive. There was some spiritual force that went into our bodies that made us animated. And unfortunately, that idea died with science. We now know that life is not a special force. It's just the end result of biochemical processes. Life is a process. So that what makes me talk and act and move and live and breathe are a series, a cascade of bioelectrical processes that accumulate to something that makes a conscious being. So there's a physical explanation for life and consciousness, I think. And that's why the soul is kind of no longer a common notion in science. It's lost in time. Okay. What about all near-death experiences being similar? Yeah, near-death experiences are very amazing things. They're incredible. The problem is, we have done studies on these things, and we find that they are typically hallucinations. They're typically dreams. They're typically things like that, along that category. And the reason why they typically tend to be similar is because our brains are similar. I mean, I guarantee you, if you ask 10 people around you, I'm sure one of them or two of them or maybe three of them have had a similar dream that you've had. I had a dream I was in a forest, walking through long grass or running away from a monster. Right? We have very similar thought patterns as human beings, so it's not too crazy to think that we'd have similar hallucinatory experiences. Now, there is no evidence that these experiences come from some other realm or somehow spiritual. They seem to be what happens when your heart stops beating, your brain secretes certain hormones that give rise to these hallucinations. And we now can actually test for these things. We now can invoke hallucinations in people. Out-of-body experiences we actually can now produce at will into people by knocking them unconscious, right? Your brain goes into different states. So there's a blurry line between your different brain states. It's not just, there's no fine line between being unconscious and conscious, and there's a lot of in between. So in this process, a lot of things happen and can give rise to these hallucinations. So, yeah, we don't know for sure, but they seem to be just dreams. Why is there such a gap between us and the closest ape's intelligence? Well, who said there is? Who said that there is such a gap between us? We're saying that, right? We are the ones saying, oh, there's such a great gap, because we think highly of ourselves. We think that we're so smart. We think we're amazing because we have TVs and cars and phones. But go back a few hundred years, we were very similar to other apes. Why? Because We lived in huts. We, didn't have any technology. We were very judgmental. We were very bigoted, very dumb, very non-intelligent back then. Let alone 10,000 years ago. 10,000 years ago, imagine a caveman. I mean, compare that to a chimpanzee. There's almost no difference. The difference comes in the accumulation of knowledge over thousands of years. We think we're so different because we have been accustomed to living in modern society where people in the past have transmitted down through time technology and knowledge and things that give rise to our current state of affairs. So all I'm saying is perhaps we are not as smart as we think we are, relatively speaking, to the other apes. Furthermore, the other apes are not dumb. Gorillas have been shown to do sign language. They have been shown to understand hundreds of words. They have been shown to play games. They can literally go on YouTube. There's a video of a bonobo playing Minecraft, right? The other apes have the precursors to everything we have, language and everything. There's not much difference. They're not as dumb as we think they are. The differences come biologically and the fact that we have a bit more complex brain chemistry. We had to adapt in different... Humans walked out of Africa. We left Africa and we migrated to other territories that forced us to think of new ways of surviving. We had to use the environment. We had to, be smart, and that's what drove our intelligence. Language was also a major factor in making us different from other apes. Language allows you to communicate, transmit data cross generations, generationally. So all these things make us human. But all I'm saying is that the dividing line isn't all that big. We are very, very similar. Okay. What do you think about dimethyl sulfide? I don't think there's life there. Now, we don't know enough to see if there's life on other planets. Even if we can definitively know that there was this type of a molecule, we would have no idea if there was actually life there. We had no idea. We'd have to go there to figure that out. We can never be certain. However, it is, I think, increasingly likely that as we learn more about the diversity of chemistry on other planets, I think the room for alien life is increasingly greater. There's more and more room. The more we look out in the universe, the more we learn about the chemistry, we're finding more and more room for possible alien life. And I think that's a good sign. I think that life could be very common out there. Now, there is a NASA program in the next couple of years called Ariel that's going to survey certain exoplanets and peer into the chemistry and definitively know what chemistry there is. And I think that's when we'll get even a better understanding of possible life out there. We can just never be 100% certain until we go to other worlds. Or scoop up a little bit of their atmosphere and bring it back to Earth and look for little microbes. But I think that it's very promising that there's going to be tons of life out there. Okay. Every time I do research on the universe, I get a panic attack. Yes, the universe can be scary. I remember when I was a kid, I'd be too scared to look under the ocean. When I was at the beach, I go to the beach and the water was murky, it was dark. I was just too scared to look under there. Even though I was swimming in it. I was swimming in the ocean, yet I was too scared to just dip my head under and look up, and look under. It's because humans fear the unknown. We innate in our bodies and our DNA is the fear of not just, you know, the unknown, but also the known. We also fear knowing too much. We fear that out there somewhere, if we know too much about things, that we will become insignificant. That maybe in all this vastness, there is no meaning, right? Maybe we'll find that, maybe, perhaps we're scared even more about that, right? Perhaps we're not just scared of the unknown, we're also scared of the known, knowing too much. So I think all these reasons are reasons we're scared. But I think in my experience, knowledge and science has only increased the confidence in my life. Has only increased my confidence levels. Have only made my life a better experience in all categories. Okay, a couple more questions. Let's see. Could there be life on an all-water planet? Yes, absolutely. Absolutely. Now, would there be intelligent life? Probably not. Intelligence in terms of like mammalian level intelligence? I don't think so. I think intelligence requires some understanding of different habitats in an open environment, an expanded area. In the ocean, you don't need, like, for example, when you're a fish in the ocean, you don't see very far, right? The attenuation length of light in the oceans are very short. You don't see very far. You couldn't, even if you had perfect eyes, you couldn't see very far because light gets mixed up in the oceans. But in the air, it doesn't happen that way. So in open air, you see very far, and you're able to see different, more diverse types of habitats. So I think intelligence is tethered to, this kind of process in which you're exploring new habitats and able to see very far. Because as a fish, you don't need big brains. You just, okay, what's this? Smells like food? Okay, eat it, right? You're just in your environment, just eating food. But when you're in open air, when you're in an open expanse, there's a lot more choice. There's a lot more things you can do with your time, and there's a lot more things you can prepare for. So intelligence, I think, requires that process. So if there was life in these water worlds, yes, there could be fish, but would they be intelligent like we? I don't think so. I think land is needed for intelligence in some way. Do you think there was life on this planet before the Ice Age? Absolutely. There have been many ice ages before us. The ice ages are cyclical. They happen all the time. Now, was life different in the past? Yes, there's tons of different species in the past that we couldn't even imagine today. In fact, many fossils, many living beings that have existed, we probably will never know of because their fossils have degraded, their bones have degraded into nothing and vanished, right? So I would suggest that the majority of living beings that have ever existed, we have no idea about their existence. And that's scary to think that there could be all kinds of life out there that we don't know about on our own planet. Do you think the government is hiding findings of alien life? No. The Clinton administration couldn't even hide a blowjob. How the hell are they going to hide aliens? It's sad to think about. All right, guys. I hope you enjoyed the live. Look, guys, I think science is important. We need people who understand it more. I'm just appalled every day when I debate. I don't see people eager to learn. I just don't. It makes me sad. It really does make me sad that people just don't care, you know? Because it's not just that, oh, come on, guys, do science. It's not just that. There's deeper implications science and understanding and literacy has on our world. You know, a lot of racism, a lot of bigotry, a lot of sexism and anti-LGBT. A lot of these things stem from science illiteracy. And I think, understanding more about each other enhances our quality of life and rights. And it's sad that people don't have the passion, the urge to learn more about them, about the world around them, the curiosity. I think we should, as a society, embrace our little quirky, quirky features of people wanting to learn more. And I think there's a lot of great things to learn about out there, and I wish I could share that with you guys. There's great value. So, yeah, science has infiltrated every aspect of my life. Science doesn't just help me in science class. It helps me everywhere. It helps my finances. It helps my career. It helps my health. It helps my relationships. It helps my social outlook. Why? Because when you follow a scientific method, when you understand what science is, it's just a method. It's a way of viewing the world, skeptically interrogating things around you, poking it, seeing what happens. When you have that scientific mindset, it begins to infiltrate and seep into every aspect of your life for good reasons, and in good ways. And that's why I do this. There's so much utility in science, and it's vastly underestimated. Also, we have so much information at our fingertips now than ever before. I mean, just a couple hundred years ago, nobody could have ever imagined knowing about evolution. Guys, DNA wasn't discovered until 60 years ago. We didn't know about DNA until the 50s. Most people, the common public, didn't know a damn thing about DNA until the 70s and 80s. Come on. There's just so much to learn out there. And we have so much knowledge today. As Einstein said, we're standing on the shoulders of giants. And we should not take it for granted. We should not take information for granted like we are today. We live in the information age, right? We live in the information age. But we take information for granted because we've been so accustomed to it. No, we have to take advantage of every piece of data we have. And instead of just letting it slip through our fingers, let's utilize it for the better. We don't even know how to use information today. We don't even know what information to know or to look at. We're so bombarded. We're swimming in an ocean of information. Everybody's so confused. We don't know how to process it. That's where science comes in and helps us. Science brings you back on track. It's a compass, right? It's like science is like a compass that allows you to navigate through this ocean of information. And that's another reason why science is more critical today. Because people, go on their phones, go on Twitter, and they'll read something and just, yeah, this guy said it. This influencer said it. Oh, he has a big following. He must be right. No. We have to be more critical about information. And now more than ever. This rings true more than ever before. And That's why I do this. You know? So. Yeah, so stay curious and keep learning. Keep asking questions, and there's lots of answers out there. Who was helped by, who enjoyed this, who learned something, who learned a lot. Whose mind was blown today? Like, whose mind was blown by all that information? Oh yeah, good job. You saw the news about 7 Dyson spheres. Yeah. I mean, it's possible. You know, Dyson spheres are these big structures that aliens could produce that would kind of suck energy from the sun, from the stars. The problem with that is, if aliens exist, why would you even want to make that thing? That's too clunky. You would have to make a gigantic structure, which itself would require energy to produce, and then you're not really getting much from a Dyson sphere. Wouldn't it make more sense to just build a star yourself? You can build a nuclear fusion facility yourself. You know, why would you want to, surround a star when you can just make your own star? A fusion, is more. Fusion would make more sense than a Dyson sphere. So, I don't know. I just could be wrong about that, but. Thank you guys for watching, and see you next time. I know you guys wanted debates, but I can't debate every day. I think that it's important to understand these things, these fundamental facts. If we don't, nothing else will make sense. If you don't understand the fundamentals, nothing else forward is going to make sense. You have to know this basics. You have to know the basics to know the complexities. It's like you can't just skip from multiplication to calculus. you need the stuff in between. You need that kind of education. But people who are religious, what do they ask? Where do we come from? Who made the design, right? The reason why they're asking these dumb questions is because they haven't taken a look at the steps. They haven't taken the steps to, ask the better questions. And that's why this is important. If you don't have a general understanding of science, you're never going to ask the right questions. And that's why, again, science helps you. Science helps you ask the right questions. It refines your ability to make questions such that it becomes efficient enough so that you don't waste your time.